All right. Here is a similar question, which अब हमारे पास हमने find out करना है whether a graph is connected when the minimum degree of a graph is bounded from below. Okay, so we say that every vertex is connected to at least half minus one of the vertices, and the claim is that the graph must be connected. Any ideas how to solve this? Yes. So we start with the same argument that you have two vertices, let's say U and V, and they are not connected to each other. Then what?
Each will have, X will have N and Y will have N minus K vertices.
Yes, but I think it's slightly simpler than this in this case. So we know that the degree of U is at least this much, and we know that the degree of V is at least this much, right? So let's say that this is the neighborhood of U, and let's say this is the neighborhood of V, okay? So U is connected to N over 2 minus 1 vertices, and V is connected to N over 2 minus 1 vertices, okay? Um, if there is a node which is in the both of these neighborhoods, so here we are done. Then U and V have a path. Okay, so by contradiction, ये neighborhoods would be distinct. Do you understand this argument? That if there is a vertex जो इन दोनों में lie करती है, तो फिर there is a path from U to V, and we are done by contradiction, which means कि ये दोनों जो neighborhood हैं, they must be distinct, which means Okay, how many vertices do we have? We have a vertex U, we have a vertex V, and we have n over 2 minus 1 vertices in the neighborhood of U, and we have n over 2 minus 1 vertices in the neighborhood of V. Okay, how many vertices do you get by this calculation? You have a short, okay, all the vertices are in there. There is no other vertex left. Okay. Now, if you pick a vertex in there, so this guy has degree at least n over 2 minus 1 because the minimum degree is n over 2 minus 1. Okay. But what it means is कि एक तो इसका neighbor U है और बाकी it must be connected to everything in here. क्योंकि ये अगर इनमें से किसी के साथ connected है तो फिर you will have a path from U to V. Are you guys following?
Yes, sir.
Sir, could you please repeat that?
Yeah, sure. Let me go back again. So हमारे पास condition ये है कि we have a minimum degree at least n over 2 minus 1, or we need to show that and we need to show that the graph G is connected. Okay. I think हमें यहाँ पे we need something more because I see a problem. So let's say कि n आपके पास 4 है, n over 2 is 2 minus 1 is 1. तो फिर you can have a direct आपके पास हो सकता है ना ये एक disconnected graph. Okay, everyone has degree, minimum degree is 1, which is equal to n over 2 minus 1. Is it true? Yeah, ना ये problem है. n over 2 is 2 minus 1 is 1. We have a disconnected graph. I think यहाँ पे मेरे ख्याल में more than होगा. More than, sorry, it's not more than equal, it's more than. Okay, so we are good. So it's not greater than equal to, it's just greater than. Okay, so we know that the minimum degree is at least n over 2 minus 1, and we need to show that the graph is connected. Okay, that's what we need to show. So by contradiction, let's assume that graph connected nahi hai. If graph is not connected, so there must be a vertex u and there must be a vertex v so that they are not connected. Okay. What does this mean? This means that since minimum degree of u is at least more than this, तो इसका मतलब ये है कि there are more than n over 2 minus 1 vertices here, okay? And there are more than n over 2 minus 1 vertices in here. So this is the neighborhood of u. These are the vertices which are connected to u, and these are the vertices which are connected to v, okay? And they must be distinct, okay? You can't have a vertex x जो यहाँ पे भी है और यहाँ पे भी है. Because if that's the case, then you have a path. You can go from u to x, x to v, and you will have a path. But we are assuming that there is no path from u to v. Okay, so that's not possible. You can't have a vertex in both of these neighborhoods. Now let's count the set of vertices. If we count the set of vertices, so we know that you have u and you have v, and there are more than n over 2 minus 1 vertices in the neighborhood of u, which means that this set is bigger than n over 2 minus 1 here plus n over 2 minus 1 in here, okay? Which means that the set of vertices is more than n, and that's the contradiction. You are done, okay? Because the number of vertices is equal to n, it's not more than n. And that completes the proof. So this was actually easier than the previous one. You start with the assumption that the degree is at least n over 2 minus 1, and you need to show that the graph is connected. You start with the contradiction that graph is actually not connected, which means that there are two vertices u and v, so that there is no path from u to v. So then let's count the number of vertices. There is u, there is v, and there are more than n over 2 minus 1 vertices in neighborhood of u, and there are at least that many neighbors of v, which comes out to be something more than n, okay? But you can't have more than n vertices. There are exactly n vertices. This is the contradiction, which means there must be something in the neighborhoods of these two vertices common, okay?
Yes, sir.
Awesome. Questions?
Sir, where do the first two ones come from in the vertices being greater than 1 plus
Yeah,
1?
sure. So this is the vertex. I'm counting the vertex u and u v as well, no? So this is the u vertex, this is the v vertex.
Okay. Thank you.
Yeah. All right. Okay, let's move on. How about this one? Guys, try to do it on your own. I can help you, okay? I can help you start, or if you get stuck, I can help you, but try proving it. You have a graph and it's disconnected. It's not connected. You need to show कि अगर उसका आप complement लेंगे तो you will get a graph which is connected. Go ahead, try proving it on paper and let me know about your ideas where you get stuck. Whenever you're trying to prove, start with the definitions, okay? When you say that a graph is disconnected, what does it mean for graph to be disconnected? It means that there are two vertices and they don't have a path in between. Okay, that's the perfect point to start your proof. Okay, try it and you'll see that the things will become clear on the way. Okay, yeah.
सर इफ हमारे पास जो है डिस्कनेक्टेड ग्राफ है तो उसमें से एक वर्टिसेस ऐसा होगा जो बाकियों से कनेक्टेड नहीं होगा कम से कम.
यस, बाकी किसी एक वर्टेक्स से कनेक्टेड नहीं होगा एटलीस्ट.
Yes. तो अगर हम उसका कॉम्प्लीमेंट लेते हैं तो इसका मतलब है कि वो जो कनेक्टेड नहीं था वो अब सबसे कनेक्टेड हो जाएगा.
उन सब से जिससे पहले कनेक्टेड नहीं था.
Yeah.
ओके, देन
मैं कुछ और सोच रहा था, सॉरी.
okay, good start. So for G to be disconnected, all it means is that you have a vertex U. It's probably connected to few of the vertices, but there must be a vertex V that it's not connected to. Okay. Now, how does this property that U is not connected to at least one vertex, that is V, imply that iska jo complement hoga that will make the whole graph connected, not just U or V. It implies that every other vertex must be connected by a path.
Sir, अगर वो G में adjacent होंगे, like the two vertices, they will not be adjacent in the complement graph.
Yeah.
So like we can find a path from X to Y in the complement as well.
Sorry, दोबारा बोले.
If the two components we're considering that are not connected in G, they will be connected in the G complement. This is how we are going about it, right?
Yeah.
So if they're adjacent in graph G, they will not be adjacent in the complement of the graph.
Yeah.
So we can find a path from X to W in G complement.
Yeah. And W to Y.
Yeah.
Perfect. Awesome. Great. So here's the proof. Let me write it down for you. And you said it correctly. So हमने ये कहा कि G is disconnected, right? This is what we know. Which means कि एक vertex है U, which is not connected to some vertex V. Okay. I don't know what V is connected to. I don't know what U is connected to, but it's possible that U is connected to some vertices and V is connected to some vertices. I don't care. Okay. The thing is, let's call the component which contains U X, and let's call the component which does not contain U Y. Okay. अब हमें ये पता है कि जो G complement होगा उसमें you will have a edge from U to every other vertex in Y. Okay, this is known. Okay, so इसका मतलब ये है कि जो complement graph है उसमें ये वाले edge तो सारे होंगे. Okay, so what sort of problem you can have? The problem you can have is कि यहाँ पे दो vertices हैं जो पहले connected थे by a path यहाँ पे, और अब वो connected नहीं है. But the thing is, let's call them, what do we want to call them? S and T, okay? But now the scenario is that S must be connected to V and T must also be connected to V, which means that there is a path from S to T that goes through V, okay? So you can go from S to V to T. Similarly, let's say that यहाँ पे दो vertices हैं, दो arbitrary vertices हैं, S bar and T bar, okay? And there is a path between S bar and T bar as well, and that's the S bar, then go to U, then go to T bar, okay? Because we know that every vertex in here is connected to U because it was not connected to U in the original graph. Okay, so that's how we prove that every pair of vertices are connected, because pick any pair of vertices, since they were if they are in X, so here they must be connected through V, If they are in Y, they must be connected through U. If one of them is in X and the other one is Y, then they are connected by an edge, because they were not connected by an edge in G, so they must be connected by an edge in G complement. Okay, so let me try to conclude the proof. In the statement says that I assume that G is disconnected, which means there is a set of vertices which are connected to U, let's call it X, and there is a set of vertices which is not connected to U, and let's call them Y, or Y contains at least one vertex, और उस vertex का नाम हमने V रख दिया है. Okay, now I'm going to show you that every pair of vertices in G complement is connected by a path. Let's say कि वो जो pair है वो X के अंदर है. If that pair is in X, तो फिर both of those vertices must be connected by an edge to V. Okay, which means that there is a path between them which goes through V. If both of them are in Y, then they are definitely connected through U by two edges. Okay. If one of them is in X and the other one is in Y, then they are connected by only one edge, which was not present in G, so it must be present in G complement. Good. That completes the proof. Questions? Doubts? Comments? Anything? Okay, so that's it. That's probably just insulting your intellect to assume that there is a confusion. This is, of course, a very easy question. If graph G is disconnected, then G complement is connected by the argument that I just gave.